Good morning. This is Mr. McMurray, and we're here ready to talk about simple machine notes. How exciting! All right, or not so exciting, depending on how you feel. It is Monday morning. What can I say? So here we go. We had talked last time we did notes about third class levers and first class and all that good stuff, and so here we are going. Okay, we talked about torque. Torque has to do with how long the effort arm is and how much force you push down on it. It makes it easier to turn the more torque you have. All right. And now we need to talk about some other type of simple machines. First of all, let's talk about pulleys. All right. A pulley basically has a rope around a wheel-like structure. Okay. That has a groove in it that holds a rope, and it's used to move objects. Okay. It's kind of a bulky definition instead of just saying, well, you know what a pulley looks like, right? Okay. So let's look at a pulley just to see real quickly here. All right. Right here is a pulley. All right. In fact, this one has a double pulley. In fact, this one has several pulleys on it. All right. It has even let's get down low enough if we can. Has a pulley at the bottom coming up. All right, and so we actually have two pulleys up there and a pulley down here. But as you can see, they all have strings or ropes that go through them. And as you pull or don't on the strings, it moves things up and down. And that's basically what a pulley is. All right, and it helps a couple different ways. One, it changes the direction of the pull. If you just have one pulley where you throw a rope over the pulley and you're pulling on it, now you're pulling with gravity, so the weight of your body actually helps you. As opposed to picking it up where you're lifting it against the pull of gravity. So that's one of the ways it helps you also. Okay, and pulleys are used, there's like what we call block and tackle, is a whole bunch of pulleys. And when you put more pulleys together, it takes less force to lift things. But unfortunately, if you pull the rope 2 feet, whatever you're moving may only move a couple inches, okay? So there's that trade-off again. It uses less force, but you're going to have to pull a lot more distance of rope through the pulley to make it work. But you can lift extremely heavy things like motors out of an engine and things like that if you have a block and tackle or a combination of different pulleys, all right? All right, so that's all we need to know for pulleys right now. Let's go to the next one, maybe. All right, some examples where you might see some pulleys. Flag poles usually have some kind of pulley, so that you're pulling the ropes to pull the flags up or down. Have pulleys. Cranes very often have pulleys when they lift or lower things on the crane. Window blinds. If you turn the window blinds, not where you turn them to open them or not, but when you pull them to lift them up or down, you usually have some kind of pulley system involved there. Okay. All right. Besides that, we also have wheel and axles. All right. A wheel and axle is basically you have two shafts that are hooked together, and when you turn one shaft, it turns another shaft. Okay. All right. So what is a wheel and axle? What are some examples? Well, obviously, on your car, you have an axle that turns. It's hooked to the wheel, and so when the axle turns, it turns the wheel. All right, since the wheel is bigger, it travels a farther distance around than the axle does. And so that's a useful one. This is a wheel and axle that we would use in classroom. All right, I have a shaft here that as it turns, it can turn these different wheels on the other side. And if they had different strings on them, they would pull it up a different amount every time it goes around. So the advantage is I turn the small one and it turns these big ones once also. Another common application of this are gears. Any kind of gears. If I turn this one, it turns that one. All right. And as I turn that one, it turns this one. And so I can either, every time this one goes around once, this one may only go around once. So or less than once. So if I turn this one, the big one, it will make the littler ones turn around faster or more times. So I can turn this once and make these turn, say, 2 or 3 times. Okay. Some are, depending on how many teeth there are, if there's 10 times as many teeth on one, it'll make the other one, every time this one turns, this one will go around 10 times. So a very useful thing there. But you're turning one shaft, which is turning another shaft. In this case, they just have little cogs or teeth that interact with each other, but you're still turning one shaft to turn another shaft. Another common example would be a screwdriver. Okay, you're turning the one shaft, which is the handle, and that is turning the shaft or the screw part of the screwdriver. So you're using it to turn and actually drive the screw in. Okay, the bigger the handle, the less force you have to use. You have a better mechanical advantage. Okay, and so bigger handle screwdrivers, besides fitting your hand better, also give you a higher mechanical advantage. Little skinny screwdrivers are necessary sometimes, but it's to get into a small screw head, but they are hard to put as much mechanical advantage on, okay, and exert as much force on. So that can be a problem with those. All right, but those are all wheel and axles, okay, not just wheel and axles like we think of with a car, which is, of course, a wheel and axle also. So when one shaft is turned, it turns another shaft or wheel or gear, depending how you look at it. Examples: a screwdriver, pencil sharpener, the old fastening kind, not the electric ones, but where you turn the handle and it would turn the shaft inside that would actually sharpen your pencil. Different kind of gears and winches and things like that will all work using the wheel and axle. All right, an incline plane. Incline plane is just a ramp, basically, that forms a right angle to the ground, okay, which we would think, well, that's kind of straightforward, but basically here. So there's the right angle right there, and so that's a ramp. Okay, that's pretty straightforward. Anything that looks like a ramp, there's handicap ramps, there's wheelchair ramps, on-off ramps, overpasses on highways are basically the same thing. You're taking a ramp to take you up and over maybe another highway or whatever, but that's basically it. Okay, so those are inclined planes. A screw is basically an inclined plane, but it's been wrapped around a post in the middle. If you look at a bolt or a screw, you have this little layer that goes around, and spirals around the screw. Okay, if we look at that as an example with a piece of paper, we could do it like this. I have a plane here. I've marked the top in blue. And if I turn it around a post, which in this case is a colored pencil, all right, I will make a spiral pattern around the post, just like the threads on a screw or a bolt. Okay. Notice if I do a flatter ramp, which is easier to go up, they're close together. If I do a bigger ramp like this, which is steeper and more hard to do, then it's going to be, the threads are going to be farther apart. You can see, and that would be a much difficult, just like it'd be harder to go up a steep ramp like this, it would be very difficult to screw in a screw with very wide threads compared to one with thinner threads. All right. So that would be a screw. So obviously jar lids are basically screws. You screw them on, screw them off. Wood screws, any kind of screw, metal screw, whatever. Switchbacks on a mountain where you go around and around the mountain, gradually going up. That was basically the same pattern as a screw. All right. Wedges are very much similar. A lot of times door stops are considered wedges. Wedges are two inclined planes put back to back. All right, so if you do it right here, so it's thick at one side and it comes to a point on the other side. One example of that, common example, would be a knife. Anything with a blade of some sort probably is going to be. It's thick at the back, but it's very thin and pointy on the other side. So it's basically an inclined plane coming from a thick point down to a narrow edge. And so any kind of blade, scissors off this, any kind of cutters or clippers are either an inclined plane if they're only tilted from one side and come to a point. If they're tilted from both sides and come to a point, then they would be a wedge. Now let's try the next one. See if I can get to the next page. There we go. All right. Now, technically, all simple machines, all 6 kinds we've talked about, can be classified as either a type of lever or a type of inclined plane. So in a way, there's only 2 main types, and everything else fits there. All right, a pulley, all right, can be considered a lever, okay? And a wheel and axle could be considered as a lever. Let's look at how that could be true. Up here. All right. If you think about this as a circular lever, if you do a line straight across here and you turn the screwdriver, the fulcrum is the middle and it rotates around that fulcrum. And so if we glued this on there, it would tilt up and tilt down. The only difference is, unlike a regular lever that hits the ground, it just keeps on going around, 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 and circular like that. Okay. The same would be true of our pulleys. Picture of one. Okay. As it goes, it just turns and turns. So this would be like the fulcrum in the middle. So it'd be a first-class lever, but it's circular, so it can just keep going and going and going and going, rather than just doing it and hitting once. All right. Maybe not. Okay. All right. Class is starting here, but basically, pulleys and wheel and axles could be considered to be circular levers, okay? And the axle, or the center part, would be the fulcrum, all right? And so they're really just a type of lever, all right? Now, what else do we need here? Let me see. Can't get the thing to work here. It's not working. There we go. All right, screws and wedges, on the other hand, are modified inclined planes. A wedge, we said, are just 2 inclined planes put together so they come to a point from the side. A screw, we pointed out, is a inclined plane that's been wrapped around a post. So really, they're just types of inclined planes. And so in that way, we could say that all 6 machines count as either a lever or an inclined plane, and they're just kind of special cases of those 2 machines. Now, if you have more than 2 kinds of machines, simple machines, then that is called a compound machine. All right. An example would be a bicycle. All right. I've got a bicycle here somewhere. There we go. Okay. And you have several things. You have levers up here on the brake pads. You have gears down here, which are like a wheel and axle. You have, of course, an actual axle on the wheel that's being driven as the chain goes around. Okay. And there are a lot of different machines that make up a bicycle. And then there's the brakes, which also have levers involved and stuff like that. So basically they do that. Scissors are a lever because they have a fulcrum in the middle where they rotate around the screw that's in the middle of it. And then they also have blades, which are wedges. So they are a compound machine as well. All right. Now, mechanical advantage, we said, we've kind of talked about this before. We're going to put it in these notes again since we haven't done it this semester. Mechanical advantage is how many times a machine multiplies your effort force. How many times easier is it to do something when you are using the machine than it is without it, okay? And so that's kind of what that does, okay? The bigger the number, it's usually just a number, and the bigger the number is, the better it is. It makes it easier to use. The ideal mechanical advantage is the mechanical advantage of a machine if there are no friction or any loss of energy, and that is the IMA, and that is can either be the effort distance, like on the lever, how far up or down the effort goes, divided by the resistance, how far up or down it goes. It can also, on a lever, be the effort arm divided by the resistance arm, which we also did in our lab the other day. All right. Actual mechanical advantage is the real world, what actually happens, and so it's actually the amount of force the resistance is divided by how much effort force we have to put to make it move. The less effort we have to use to move a bigger weight, then the bigger the actual mechanical advantage. And since we're actually measuring the actual forces we use, it's actually measuring exactly how much it helps us. Okay, that's it for the notes. We will have a quiz tomorrow, and we will see you then.